Back in section 1.1, we talked about functions, and we talked about ways that we can describe relationships. We talked about the fact that functions have one input, determining exactly one output and only one. And we're going to encounter our first type of function today, and it's linear functions, aka lines. And you guys have been working with lines since probably Algebra 1, somewhere in late junior high or early high school. Okay? What we're going to do, however, is we're going to be taking sets of data, information, like real life information, and forming a line to fit that information. Now, I will say that some of you may have seen how to do this with your calculator before, maybe not in depth. I know that the pre-calculus class that my son is in high school has a component of it in his class. I've shown him his eyes glaze over. I've shown him his eyes glaze over. He still doesn't know really how to do it. Maybe that's you. Or maybe your teacher really went through it thoroughly and you do know how to do it. So if that's the case, then you are ahead of the game. Okay? But we're going to work with very much calculator stuff today. The other thing that we're going to work with is a lot of interpretation. How to take what we are given or what we've created and figure out what it is we really have. Right? So to start with, there are 4 elements of a model. We're going to do linear models today, but next time we're going to do a different kind of models, and we're going to be doing several different kind of models, but today linear. But all models have these 4 components, at least the first 3. The first thing they have is an equation with a name. So what do I mean by name? I mean that it should say something like f of x equals, and then you're going to have an equation. So the name is f of x, or g of x, or whatever. It's going to have a name. Second thing is it's going to have a description for the output with units. So when we write the equation, right after the equation, we're going to say the word like dollars, or people, or 1,000 pounds of food. It's going to be what is the output, and we're going to write it down. Third thing is that we're going to write down what the input is and how it's determined with units. So something like where x is the number of years after 2000, where x is the number of people that showed up for the ball game, where x is in a description. Okay. The last one is a sometimes thing. It says when possible. It's going to be possible most of the time, but maybe not all the time. What this is going to do is that if you're given some information in a table, it's going to say that we know that this information is legal and valid and appropriate from the first x value in the equation to the last x value in the equation. And after we get out of that table's values of x, it may or may not be an appropriate equation. That's the idea. So you end up with an inequality, much like this one over here on the board. Okay? So you're going to have one number less than or equal to x, less than or equal to another number. Okay? So let's do the basic model for, or basic equation for a linear model. Linear models that you've seen before would have been something like y equal mx plus b. Your calculator uses ax plus b, so that's the one I'm using here. Not that it really matters. A, m, whatever letter it is, that's what we've got. So a linear model is f of x equals ax plus b, where a and b are constants, i.e. numbers. Okay? As we're working, your book is going to consistently use 3 decimal places unless it says something otherwise somewhere. So inside of a model, as we're writing things down, we're always going to write down 3 decimal places of accuracy. Okay? So we'll have something like f of x equals 3.267 x plus 4.398. Something like that. That will be the equation. The slope, or the rate of change, is the slope formula that you've seen before. Right? y2 minus y1 over x2 minus x1. The first way that you see it written here, f of b minus f of a over b minus a. It's 2 y values subtracted divided by 2 x values subtracted. And before we get too far along, let us actually give an example in their form of what this would look like. So this would be an example of a model. The cost to rent a newly released movie is c of x equals 0.3x plus $5. Okay? So you see that we have a name, c of x. Your book also likes to use the letter of what's going on, c for cost. That's why they used c. You don't have to, but that's what they're going to do a lot of the times. The next thing you see after the next thing you actually see is the equation. Then you see what the output is. The output of this equation is dollars. So they write down dollars. And then they describe the input. The input is the number of years after 2010. It's absolutely critical that you write that. Because if this isn't here, and somebody says, well, how much does it cost to rent a movie in 2017? You won't know what you need to plug in for X. Do you plug in 17? Do you plug in 7? Which is what we should, right? That's the way this is actually written. Do you plug in 2017? You don't know. So if you don't have this piece of information at the end, then you have no way to be able to use the information at all. That's why it's so important. All right, so let's actually answer a couple questions about this. What is the slope of the line that's defined by this equation? What is it? Yeah, 0.3. Okay, so that's the slope. It's the number that's multiplied by x. Our second question is to write the rate of change of the function in a sentence of interpretation. So let me show you what that looks like, because we haven't done that yet. So this is actually telling us that the cost of a movie, or of renting a movie, that's better actually. Wasn't it renting? Yeah. The cost of renting a movie is increasing. Why do I know it's increasing? Any ideas? Good, because the slope's positive. 0.3 is a positive number, so if I put in 1 and then I put in 2, the next number 2 is going to be bigger than the number 1 because the slope's positive. So it's increasing by, what does that 0.3 mean? Let's go back. Oh, it's up here at the top actually. I left it on here. Do you see my units right here? We know that slope is the change in y over the change in x. What are my units on y? What are the output units here? Dollars. This is an amount of dollars. What are my input units? What are my x values here? Years. It would be what?
It would be $0.3 over a year.
Yes. So it would be increasing by 30 cents or $0.3 per year. Right? So the idea is that if this year it's $1, next year it's $1.30, and the next year it's $1.60, and the next year it's $1.90. That's what that's saying. Increasing 30 cents per year. That's it. You're giving an interpretation for what the slope means. The slope is telling you how the output is changing compared to the input. The output here is dollars, the input's years, so it's increasing by 30 cents per year. Yes?
Does the 5 have to do with that at all?
The 5 has to do with where it starts. So like if I plug in x equals 0, then I'm going to get 5, right? So 5 would be like the value in 2010, because this is being measured since 2010. So it's the starting value. Yeah, but it doesn't affect the slope. The slope at the beginning is unchanged by the starting value. All right, so let's take a look then. Oh, I should have waited to answer your question because it's right here. Man, very good job. Evaluate and give a sentence of interpretation for f of 0. So if I do f of 0, it means that I'm plugging in 0 for x. So f of 0 is 0.3 times 0 plus 5, which gives me 5. And it's $5. I mean, that's the whole deal, is that this is a value of the money for this. And then, so that's the evaluation part. And then it says to give a sentence of interpretation. That is, what did this find? So what does 0 mean in the context of this problem?
It's 2010.
Yeah. So in 2010, what's going on? The cost of renting We could say a newly released movie, but that's a lot of writing, so I'm just going to say the cost of renting a movie, okay? The cost of renting a movie is $5. All right, so let's take one that's giving us some information, but doesn't actually give us an equation. In 1999, 28% of births were to unmarried women. In 1995, 32% of births were to unmarried women. Write a linear model for the given rate of change and initial output value. Okay, so let's actually talk about, there's two things we're going to need. It says rate of change and it says initial output value. So let's do the rate of change first. What is rate of change asking me for? What does it mean? Slope. So when you see rate of change, you should think slope. I need to find the slope. So as I'm finding slope, I need to figure out which pieces of information they're giving me are x and which pieces of information are y. Almost always, years are x. Okay? We may come across some random weird one where that's not true, but it's like 99% of the time. Okay? The year doesn't change based on the unmarried women having babies. That's not what's going on. Okay? The year just progresses on its own. That's the idea. So we're going to have the years on bottom. The years 1999, I'm just going to do the larger one minus the smaller one, although it doesn't really matter. If I did it the other way around, it'd be okay. What does matter is that the numerator's order matches the denominator's order. So in 1999, what was the percent? 28. So the 28 has to go with the 1999, which I listed first. Okay, so since I put 1999 first, 28 goes first.
But it doesn't matter if you have the same numbers, correct?
Right, like if you put 95 as your first number in the denominator,
You get that 30.
then you're going to have the 32 above it. Exactly. So we just want them to match. So if I let them go in this order, what is the numerator going to give me? It's actually negative what? 4. And the denominator is 4. And if I divide, I get, negative 1. And in terms of units, I've got percentages on top, and I've got years on bottom, right? So this would be percent per year. Now, it didn't ask me to interpret this, but if it had, like on the first problem, the interpretation would go something like this. The number of births to unmarried women is decreasing, right? Why? Because this is a negative. It's decreasing by how much? By 1% per year. And then it would probably be a good idea to clarify when that's happening. From 1995 to 1999. Okay? So that's what that would look like. Now, we weren't actually asked to do that. We're actually asked to find an equation, a model. So in a linear model, you need a slope, right? Our goal is to write this as f of x equals ax plus b. We need a slope. We've got it. A is negative 1. We found that. B is the starting value. So which of these two values makes sense to be the starting value? 1995, because it occurs first, right? So the lower value would be our starting value, and the lower value then would be the 32. So as I'm writing my equation, f of x equals negative 1x plus 32. That's the equation, that's the name of the equation, but that's not everything I need for a model. What's the next thing I need for a model? I need units of output first. Yeah. What's the output in this equation? The percent. I mean, it's only one of two things, percent or years. Which one is the output? It's percent. So you can write percent, or you can write the word percent, or that is, you can write the word percent or the symbol percent. Percent. Okay. The last thing I have to do is I have to talk about how x is being determined. what is it, if I'm asking you now, what happened in 2000? I need to know what number I'm supposed to be plugging in, right? Well, it's where x, what is x? It's a number of years. So x is the number of years since the starting value. So what was the year associated with the starting value? 1995. See how I wrote the other part of it. Okay, and then the last piece said that we were supposed to put an interval when it's appropriate. The interval here that we know that this applies to is from 95 to 99. Okay, so we're going to write that. Where, let's see, 0 is less than or equal to x is less than or equal to what? If 0 is the year 1995, what's the year, that's right, the year 1999 would be the year 4. That doesn't mean x couldn't be 5. Or even, negative 2. It just means that if we go outside of the 0 to 4, the answers we're getting may not be as accurate. We don't know how accurate they would be. But if we're between 0 and 4, we're going to be pretty accurate. Okay? Any questions on this one? Okay, I've mentioned it at least twice now, this idea of going outside the interval and staying inside the interval. There's actual mathematical names for that. When we stay inside the interval that we're looking at, that's called interpolation. So using the model to predict an output value within the interval of input. So in the last problem, if I let x equal 3, that would be interpolation. Extrapolation is where we go outside the interval of input that we're given. So if I had let x equal 5, that would have been extrapolation in our last model. It's not like one is good and one is bad. We can just rely and feel a lot more comfortable that our answers reflect reality when it's interpolation. We are feeling less comfortable when we're extrapolating because we have more chance of being wrong. And I don't mean wrong in terms of a textbook. I mean wrong in terms of I'm giving the wrong information to somebody about what really happened or is going to happen. Does that make sense? So extrapolation is simply just a less sure answer that it's going to be really correct. Okay, did everybody get this one written down for interpolation and extrapolation? Okay. We're going to use that model we just created. So the model that we just created was what? Just a second. Oh, there's a typo on my piece of paper. I'm like, what am I looking at? This doesn't look right. All right, please, yes, go ahead.
fx equals negative 1x plus 32.
Excellent. And this is percent, and where x is years since 1995, right? Okay. And then we're going between 0 and 4 if we're interpolating. So the first question says, what is the percent of births to unmarried women in 1998? So I have to use my model and the language that I wrote surrounding my model to decide what x would be. So if I'm trying to find part A, what would x be? 3. So we're going to plug 3 in. And what are we going to get? $29. 29 what? Percent. 29%. So the percentage of births to unmarried women in 1998, using our model, was 29%. How about 2005? I think somebody said it. 10. Why is it 10? Yeah, yeah, 2005 is 10 years after or since 1995. So if I plug 10 in, this is negative 1 times 10 plus 32. What do I have? 22%. Now on part C, it simply asks me to decide if the answers that I found in part A and part B are interpolation or extrapolation. So on part A, was that interpolation or extrapolation? It was interpolation. And how about on part B? That was extrapolation. And it all had to do about whether the numbers were, you can think of it as either being between 1995 and 1999 or between the 0 and the 4 for the X input that you used. Okay, so this is the part that I was telling you about at the beginning where your calculator is super duper important. And you've got it all written down. I'm just going to verbally go through this with you. A few of these steps are not steps you repeat every time you do this process. So that's good. Because I think there's 23 steps written down or something like that, right? And I don't want to do a 23-step problem every time I have to do a problem. Do you? No. No. So let's do a few things to get our calculator sort of set up appropriately as we start. So the first thing that I'd like for you to do is to find on your calculator the Stat button and press it. Okay, so the Stat button is in, kind of the middle right beside the up and down, left and right keys. Right here. Okay, so you're going to turn on the calculator, clear things out if you want to, press Stat. Your Stat menu has an Edit option, so you're going to click on Edit. And what we're going to do, I'm just going to walk you through, I'm not going to actually do a problem, I'm going to walk you through the list of steps. What you would do, and what we will do in a minute, is we will have data, X values and Y values, and we plug them into these lists. This is not the same table that's in the graph, okay? Like when I hit graph on the calculator and I have the table in there, I've got a column that says X and a column that says Y1 and Y2 and things like that. This isn't the same one because notice the column headers say L1 and L2 and L3, right? Does anyone's calculator not have L1 and L2? Okay, everybody that's looking at it says L1 on the first one and L2 on the second one. Okay, if they disappear, the reason they'll disappear is because you arrowed up here and you hit delete. You don't want to delete the L1 and L2, but if you do, I can recover them. Okay, so don't freak out if you delete them. Just let me know and I'll come over and I'll show you how to fix that. Okay, so that's the first thing. So we're going to put information in these lists. So if there is information in your lists already, does anyone have any information in there already? You borrowed a calculator from someone else? Okay. So what you do is you arrow up on top like I just did, arrow up to the L1. You don't hit delete, but you press clear and enter. So information, like it said this maybe, and I want to clear it out. I go up to L1. I press clear, which is right over here, and enter. And it clears out the list. Because that's how you delete information out of this. You can also type on top of it, as long as it's not, too many entries or something like that. The other thing that you can do is you can delete these individually by just hitting delete on top of the numbers themselves. But clear is faster because it clears out the whole list instead of delete, where you have to do it multiple times. Okay? So this is how you would clear out a list. Start from scratch. You enter your data into the list. And then you get out of this screen. So pretend for a moment we entered data. Let's go through the next steps. You get out of the screen by hitting second and mode. You can see above mode it says quit. Get you back into your regular screen. All right. Once you've put the data in and you've exited that screen, you hit Y equals. Clear out anything that's in there if you'd like. Don't need any of that there. So you've got a blank screen. A couple things in this screen. The first thing is you want to be able to see the data on the screen that you put in. Basically what we're going to do is we're going to look at what's called a dot plot. You're going to put a whole bunch of points in, you're going to look at the points. So how do you do that? Well, we're going to go up here to the plot one and we're going to hit enter on it. And my plot's turned on. It's highlighted in black. It is turned on. Okay. let's see. If, when you're doing this later, the dots don't show up the way that they need to show up, you would actually go through steps 9 and 10, or step 9, which is to make sure that the X list is L1 and the Y list is L2. We can actually check that real quick. Let me think where it is. No.
So, wait, for 6.
Oh, I know where it is.
You don't press second y equals, just y equals
For what?
for step 6?
Second Y, oh, that's what I did wrong. Thank you. That's where I was going, is actually second Y equals, turns your plots on. Thank you so much. I didn't hit that. That's why I didn't look right. If I hit second Y equals, you see where it says plot on? I already did that. I turned it on. If I hit enter on top of number 1, there we go. There's my list. X list is L1 and my Y list is L2. Does anybody's lists not say L1 and L2? So we're all set up with it saying, it looks like my screen. Every screen looks like this. Okay, the only thing on the screen that should look any different, like you need to make sure you're on this particular plot right here. List has to be L1, this list has to be L2. You can change this between these 3 different options. My favorite is the one that's selected right there because I think it stands out the most when I look at the graph. But if you want to change it to one of the others, you could. Okay. All right. You don't have to do that every time. That will already be set up for you automatically now. You don't have to do anything with it. So steps 6 through 9. Put a little arrow beside steps 6 through 9 and say, I don't have to do these steps every time. Okay? We've already done them. Step 10 is hit to Y equals. I had skipped ahead. So to hitting Y equals now, it should be turned on the plot, or the plot should be turned on the top. And you should clear out any equations. I already said that. And you're going to try and see the dots. Now, it's not going to work here because we didn't put any data in yet. But the way that you see your dots is you select zoom, and it's actually zoom 9. 9 is zoom stat, and it will show you the dot plot. Okay, so we'll look at the dots. This will show you the dot plot by hitting zoom 9. Once you've seen the dots, back in your regular screen, Y equals screen, you're going to press stat and calc. So arrow over to the right-hand side for calc. And option number 4 says lin-reg. That's linear regression. It even says ax plus b, just like we were using on the screen before, right? That's the one we want to pick. So you're going to press number 4. It's going to show up. Actually, I don't think I hit y equals. Let me try that again. Stat calc. Oh, that's fine. It does show up there. I'm sorry. Stat calc. Number 4. Lin-reg. And then you're going to tell it that you want it to put it inside of y equals. You want to put it in there so that you can graph it and see that it actually looks okay. So what you do is you hit vars, it's a variables key. It's a y variable that we're looking for, so we're going to arrow over to y vars. We're working with functions, so that's number 1, and we're going to plug it into y1. Now, if I had data in here and I press enter, it's going to work. If I hit enter right now, it's going to tell me error, 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 you don't have any data. I think it's going to say something like error domain is what it's going to actually say, but because I don't have any data in there. Okay? Once it did that, it would plug the equation into y1, and I'd be able to graph it, and I'd be able to see a beautiful line on top of my dots. So we're going to do an example where we get to see a beautiful line on top of some dots. Okay? So that's what we're going to do. Let's go on to the next example. Table shows the number of motor vehicles for county from 1994 to 1998. So I am not going to change my screens back and forth because I know you guys have this to see with me, right? You've got your notes beside here, and I want to make sure you're seeing the calculator screen as I hit buttons. So I'm going to leave this on the calculator screen. So the first thing you would probably like to do is to understand that putting in the numbers, slow down because some of you are already doing it. Wait. Putting in 1994, 1995, 1996 is a bad idea. Because there are functions we work with and it will create what's called a memory overflow in your calculator. It doesn't like big input numbers. So we don't want to put in 1994, 1995, and so forth. My suggestion and general rule of thumb is to use the last digit. So we would do 4, 5, all the way up to 8. So I'm going to put in my stat menu. So the way we go about this, remember, is by hitting Stat, Edit. Okay, and we're going to put in 4, 5, 6, 7, and 8. Okay, don't use the actual years. In Y2, or L2 rather, you can put the values that it gives you. You don't ever need to change those. So they're fine to do 108, 122, 137, 155, and 169. Okay, so L1 has the years with the last digit only. L2 has the millions of dollars. So far, so good? We're all good with that, yeah? Okay, you're going to exit out of this screen by hitting second mode, second quit. And I'll go through it again. I know it was already on my screen, but we'll pretend like it wasn't. We get that model by looking at well, let's look at the dots first. We didn't do that. So if we hit graph, or hit Y equals, the plot one's on, and we're going to hit zoom 9. And zoom 9 shows us a dot plot. We see all the dots that we just put in there. And do they look fairly linear? They do. So this is a reasonable thing to do for this. If they were all wonky all over the place and you try to fit a line to them, it's not going to make a lot of sense, right? But this works. Yes?
Why does yours not have a line in code that mine does?
You've probably got something in Y1 already. Hit Y equals and clear out anything that's in the Y equals menu.
No, I haven't.
Okay, I'm going to take a look. Does anybody else's screen not look like this? Okay, is everybody else's screen okay? Looks like this? No, one more is not? Okay. Anybody else having a calculator not look like that? We're all good? Okay. Exit the screen, so second quit. You're going to hit Stat, Calc, number 4, vars, y vars, function y1. Stat Calc option 4, vars, y vars, function y1. And then you can hit enter. And this is the A value and this is the B value for your function. Yeah.
My calculator doesn't do it like that. It goes to the
Okay. I don't know what happened, but I'll figure it out. That works. Okay, let me see yours. Okay, I think it says for regression, then you hit stars, y bars, function, y1, and then enter. Okay, so some of the newer TI-84s are making you go through where it says, bottom it says store regression equation. and you tell it y1 there. So it's just a little bit different on the data entry, but it still works. Yeah, still working. You've got an equation. You've got an A value of 15.5 and a B value of 45.2. I want you to hit graph now, just so that you can see that it actually is a reasonable equation to fit the dots. Okay. So back over here, it says to find a model for the data. This is the part where we actually write down what we found. We need a name for our equation. And just so that we can say we did something like the book did today, I'm going to call it A for amount. Okay? A of X. You can call it whatever you'd like. S and L are not good choices because S's look like 5 and L's look like 1s. T's are really bad as well, but other letters are fine. So A of X equals. We want to model this as AX plus B. What was the A value that your calculator just gave you? 15.5 X plus, what was the Y value? 45.2. What you just did was all the calculator component of this, right? The next thing you're doing is the language component. You gave the function a name, and you wrote down the equation. You've only done about half the work, maybe not even quite. Because the next thing you need is what? Do you remember? Not yet. Inputs last, output first. Okay, so we write down the output units first. What is the output of this function? It's millions of dollars. So we're going to write down $1 million. And then we're going to do the input. So we were going to do the input before. You say where X is. What did we do when we actually put in our X values?
Put the last digit in.
We did. So we let the year 1994 be represented as X equals 4. So what would X equals 0 be?
1990.
It'd be 1990. So we're measuring our X values as numbers of years after 1990. So we have to write that down, where X is the number of years after 1990. One more thing to do. What is it? Put the input interval, or write down the input interval, which was 4 to 8. If you don't have all the pieces, points have to come off because you can't use the information that you found. So if you leave off the output, it doesn't give people very much information. If you leave off the input, they can't plug a number in. Okay? So all the pieces need to be there. The second question says to estimate the amount collected in 2000. What would we have to do to find the amount collected in the year 2000? Right, we need to plug in a number, and since it's years after 1990, this would be the number 10. Now, I already showed you, and you already know, that what this actually looks like is 15.5 times 10 plus, what was our other number? 45.2. And this one's not too bad. I mean, like, we could enter that by hand, and our calculator is not going to take us very long. Agreed? But wouldn't it be nice if this was an ugly, terrible, gross-looking equation that I just had to write down, to not have to type it all back into the calculator? It would. And in fact, because we've done things the way we've done them, our calculator is handy-dandy, and it can do that for us. In your calculator screen right here, if you will hit second and graph, you'll pull up the table, which we've done before, and you can simply put in 10. You can arrow over on top and you can get the output when x is 10. Now there's some caveats to the outputs. They have to make sense in terms of the context of the problem. So this one's in millions of dollars, right? So it would be okay to have decimal values, right? I mean, it would even be okay to have 3 decimal values because it's millions of dollars. If the output were only in dollars, how many decimal places could I have? Just 2. What if the output was, say, numbers of people? No decimals. So the number of decimals in your output will be 3 unless it doesn't make sense for the context of the problem. Here it does. It's totally fine. So if I plug this in, and I see I have 200.2, then my output is going to equal 200.2 what? Say it loud. That's right, $1 million. Yep. So this will be $1 million. You can either put the dollar sign at the beginning or write the word dollars at the end. Either way. Okay, it's $1 million. According to the model, I should stop. Does anybody have any questions on that step? Yes, sir.
Why doesn't when you plug in 10, why doesn't it add up to the 200?
Because it's the value at the year 10, not the value from the year 0 to the year 10. We're not adding up the different values. We're just finding, what was the context here? The amount of motor vehicle taxes in one specific year. Did you put the 10 in and it give you this?
No. I got 109.8.
Oh, no, that shouldn't work. Hang on. Let me see if I do. Mine says 200.2. There's maybe a typo. Double check.
Okay.
Because mine does say 200.2 when I plug it in. It should. It should give you the correct
When you plug
value.
it in the function?
If I plug it in, like if I type in 15.5 parenthesis 10 in parenthesis plus 45.2, it actually works as 200.2.
Okay.
To work?
Yeah, my fault.
That's okay.
I had a minus.
Not a problem. Okay, part C. According to the model, when will the amount collected be $300 million? And under what conditions will your answer be accurate? So we got two, kind of, this is like a double question, right? Start with the first part. When will it be equal to $300 million? What is this asking me to do? Yeah, you're right. It's asking me to plug in an output, right? It's asking me, when will this equation's output be equal to what? 300. Remember, your output is in millions, so I'm looking for this to actually equal to 300 because 300 means 300 millions. Okay, so this is where all of the work that we've been doing with the outputs equal are helpful. If you hit y equals, the equation that we've already found before is in y1. You didn't have to enter it, it did it automatically with our other steps. And in y2, you're going to type 300. Now, it's not going to actually show up in our graph because our graph stopped basically at the year 8, and that was before we ever got to a $300 million something, right? So this makes sense. We need to actually make our window bigger. So we're going to hit window. We'll just do window. We know that our x value needs to go bigger than 10 because in 10 we got 200, right? Roughly. So it needs to be bigger than 10, so maybe we'll do 15. We're just guessing. We don't really know. And we know our y max needs to be bigger than 300 because we want it to equal 300, so something bigger, maybe 350. And we're going to hit graph and hope that they cross, and if they don't, we're going to adjust the window. And they didn't quite, did they? I just need my window longer, correct? The height's okay, yeah? I just need it longer. So what am I going to have to change when I hit window? The x max. Right now my x max is 15. What would you like me to try? 20. Okay. We'll change 15 to 20 and hit graph. And they cross. So you tell me. How do I find out where those guys cross each other?
Trace.
You can trace, and that will work, but you get an approximation when you trace.
Second
Second trace, which is calc, we'll find the exact location. So number 5 is intersect. First curve, it says y1 at the top of my screen, that's good. Second curve, it says y2 at the top of my screen, that's good. Guess? Well, they're only crossing in one place, so I don't even really have to be close. I can just press enter. Super cool. And it just moves itself right on over there. What we need to do is we need to first write down what x equals exactly with 3 decimal places. This says 16.439. That's what it says, right? 16.439. So as I look at that, I need to figure out what's the answer to my question. What did the question ask? It said, according to the model, when will the amount collected be 300 million? And the answer is 16.439. But what is 16.439 telling me? What is it? Okay, it's getting.
16 years after.
Let's say it that way. I like that. Okay, tell me, say that again. 16 what?
16 years after I started.
Yeah, and we can certainly have a portion of a year. Is it okay to have a decimal point of a year? Sure, it just means you're in the middle of the year as opposed to being like January 1st, right? Okay, so this would be the number of years after what?
1990.
Yeah, after 1990, because that was our x equals 0 input value. So this would be in the year 2006, right? 2006, somewhere in the year 2006. The other part of this question says, under what conditions will your estimate be accurate? So the conditions that it's referring to is the fact that, let me see how I wrote it before. I didn't. That's not good. My notes don't have part of my answer in them. Oh dear. The condition is that the rate or the we'll say it this way. The model continues to hold. We'll say until 2016. This model's got to keep working. The rate of change has got to stay the same. It can't change. I can't have a huge jump up, a huge jump down. I can't have anything drastically different happening than what was already happening in general. Does that make sense? Because
2006 or 2006?
6, thank you for fixing that. 6, yes, 2006. I mean 2016 would work, but it might be overkill, yeah. So it needs to be holding and continuing to work until at least the 2006 area. Does it have to? Where is this model for sure going to be accurate? 94 to 98, right? Or 99 or whatever it was that my ending value was. It didn't have to actually work out to 2006, right? Okay. All right, we're going to do another data entry. Practice one more time. This one shows the first class postage rates for mail up to 9 ounces in 2000. First class postage rates in the year 2000. So your weight for a 1 ounce package is 37 cents. 2 ounces is 60 cents, all the way up to a 9 ounce package, which is $2.21, okay? So grab your calculator. We're going to practice these steps one more time. Now that you have data in, you even get to practice clearing your lists. So I usually clear out my y equals at some point, so I'll just clear it out right now in my screen. You hit Stat, Edit. You can either hit Delete on all the numbers in the list, or you can arrow up on top of the list's names and hit Clear, Enter. Clear, Enter. Or you can just type on top of them. That'll be okay. We've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. In L2, I have 0.37, 0.6, 0.83, 1.06, 1.29, 1.52, 1.75, 98, and 221. The list should always be the same length, or you've missed some data entry somewhere or doubled something up. Okay, if you hit y equals, if you didn't already do so, go ahead and clear out anything that's in y1 or y2. Make sure that plot 1 is on. And hit zoom 9. Does it look like a line? Yes, it does. So it makes sense that we're creating a linear equation. So let's create the linear equation now. Back in your regular screen, so you can hit second mode. Take you back here. You're going to do stat, calc, for vars, y vars, function, y1, and hit enter.
So what do you do if it was the K84?
Right where it says store regression equation, down here, just tell it bars right here, bars. And there it is, and you can click down more and calculate, and hit enter. Okay, did everybody get these values?
What do you
Down to store regression equation? Okay, you're clear out the list. So you can put a second, and it's all on this right there.
Oh.
Okay, now let's get rid of bars, y bars, function, y1. Okay, anybody else not getting to this list, they're not getting to the screen in front of us? Oh, do I have more papers? Sorry, thank you. Okay, so you've got some data values now here for your slope and for your starting value. So we're going to write down, I'm going to call it P for postage. P of x equals 0.23x plus 0.14. All right, I'm not going to flip back and forth between my screens for the moment because I'm just going to put this back on in a second. What do I write after I write down the equation? The output units. And what are they on this one? Dollars. Where x is what? What was x on your paper? What was it? The weight in ounces. Yeah. Where x is the weight in ounces. And our input interval then would be, yeah, on here it was 1 to 9. So 1 is less than or equal to x is less than or equal to 9. Part B asks us to figure out what the package price, or the postage price rather, would be for a 12-ounce letter. So what do I have to do? Yeah, I can put in 12, and I can do that by hitting second graph. You can delete it if you want, or you can just type on top of it 12. And if I arrow over, it will tell me very clearly, in case there's any repeating decimals or anything like that, the actual value. This would be 2.9, which is what? $2.90.